So what do we do today? We look at the assignments. I was hoping that you guys submitted a little bit earlier on so that I could see what you came up with, but apparently the last 10 minutes were rush time. I got most of the submissions at the last time. So I guess I will bring up your solution next on Thursday. If anything has done something clever, smart, beautiful. Or maybe if you want, you can tell us and we look at it later today. So first we look at the solutions of homework 4, and then I present homework 5. And then on Thursday, probably not, but Tuesday I'll try to assign the final project. Well, so the assignment was Cholesky, and I hope you really add Cholesky sink in, because the next assignment will be on Cholesky. So I hope you understood this. What we had to do, we had to write some MATLAB code that mimics the algorithm as closely as possible. Okay, I have not prepared, so let's do it together. Desktop, edit my Cholesky. Oh, there is a my Cholesky. Yeah, but this is clearly not Cholesky, because I don't have so many matrices in Cholesky. Okay, so since I have it, I'll use it. Instead of writing a function, I'm just going to write a script to get an idea of what I want to do. First off, I have to create a symmetric positive definite matrix. This is easy. Rand n, and then we do m equal m plus. This is a symmetric. Now we put some diagonal dominants, and this is a symmetric positive definite. Okay. And then, how can I comment everything at once? Comment. Thank you. Okay, so far we have a symmetric positive definite matrix, and I want to partition it in 2 by 2. Why would I want to do that? So let's move this. I want to do that because I want to mimic this instruction, this partition command up here. So how do I do that? With my FLA part 2 by 2, which is a function that, let's say, I defined. So first of all, I need to, so, okay. I need to change the path. Only J works libs. Yeah. Okay. So what does this function here do? It's a function that takes a matrix, which should be M, and partitions the matrix in 2 by 2. It says it here. And I have to specify the size of one of the quadrants. We said that one quadrant is enough. So I say that the, this is annoying me. I say that the top left quadrant is going to be 0 by 0. As a result, I will generate 4 pieces, and so I put 4 pieces here in these 4 matrices. But since I start from M, I want to call them M. And let's see what happens. So my chol. Of course, I didn't print anything. Let's maybe print something smaller. And let's print M top left. What do you think M top left will be? Come on. Everybody knows, right? What do we expect M top left to be? 0 by 0, empty, nothing. And that's what I get. So let's see if I created everything. M top right, M bottom left, M bottom right. So top left empty, top right 0 by 4, bottom left 4 by 0, and bottom right is the whole matrix. Now this is the matrix and clearly bottom right. So that's a good start. And how did I do that? With this partitioning. If we want, we can look at what the partitioning is. It's nothing else than a just big if statement, and the if statement tells me which quadrant I am identifying. Top left, okay. I have another case where I say top right, bottom left, bottom right, and then I just say, okay, if that is 0 by 0, then blah, blah, blah. I know. So that's a function. So that's a good start. Now, before worrying about computation, let's try to have the repartitioning and the continuous statements in place. So what do they have to do? They have to let me traverse the matrix. I want to start with A top left being 0 by 0, and then at the end of the iteration I want A top left to be B by B, and then 2B times 2B, and then 3B times 3B, and so on. So here we go. While the length of M top left is less than the length of M, let's do some repartitioning. How do I uncomment? Like this. Now you should notice the elegance. Since this object here spits out 4 guys, the 4 guys are aligned as a matrix. You're laughing. I'm failing you for sure.
I have a somewhat different solution, which I think is way more elegant than this.
Okay.
But that's my
I like to see different approaches. So you don't have the 9 objects?
No, I have 3 indices, and then I use MATLAB index notation to access A. So I have I1, I0, I1, and I2. These are the 3 parts that we partition our matrix in, and then I compute these every time. In each iteration, I compute.
Whoa. Which 3 parts? You mean?
Yes.
Okay.
So I have 3 indices.
1, 2, and 3. Okay.
Yeah, 0, 1, and 2.
Mm-hmm.
And I compute them, and then I use MATLAB's notation to access these indices.
Okay. Yeah. I like that too.
Yes.
So I guess maybe we can look at other solutions later. I like that too. Let's continue with M. Here is the repart. The repart tells me that we start from 2 by 2 and we go on to 3 by 3. So what are the input arguments? The input arguments is whatever defines the matrix. These 4 guys that I obtained from here, they define the matrix. And then once again I have to define the direction. Now I say that I go towards the bottom left, bottom right actually. And I take out whatever I want, B by B or 1 by 1, 2 by 2. Let's start with 1 by 1. So what is going to happen? M00 will be M top left. This will be just a copy. M11, M12, M21, and M22, these four guys will come from M bottom right. And I know that M11 is 1 by 1. So the specification here is always for the middle guy. And bottom right tells me from which quadrant is generated. And then in correspondence to that, I can trash all of these. And then since we want to make some progress, I should uncomment this. All right, and now it's a matter of putting the guys together in the right way. So if I go towards bottom right, this thing should be in top left. And to see if anything is happening, for instance, we can look at M11. Let's also look at M. Okay, so we create a matrix 4 by 4. And N11 at the first iteration is this guy, second iteration, third iteration, and fourth iteration. It looks like we are doing exactly what we want. Let's just do another test. So now I'm plotting M00. You guys tell me what I'm going to see out of this matrix. Notice that now I will look at the M00 at all different stages. So what are we going to get? You tell me while I get a dress.
At first, nothing.
Mm-hmm.
Then 1 by 1, 2 by 2, and so on, until we have the whole matrix.
Okay, 1 by 1 will contain what?
Will contain 5.13.
Okay. And 2 by 2 will contain the 2 by 2 leading, 2 by 2 leading, 3 by 3, and so on. Yeah, I hope this happens. And the numbers now 4, 5, ta 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 ta. Okay. Sorry? Yeah, it doesn't do the last one. Why doesn't it do the last one? Yeah, precisely. Because here we say keep doing it until as long as you are less, strictly less. So we don't really go to the last one. Okay, now we can take care of some math. Oh no, wait. Maybe we can try this. Let's plot, for instance, M10. What will I see? So now we go in steps of 2 by 2. Our matrix is 6 by 6. What do we see? At least at the first iteration. Yeah?
2 by 0, 2 by 2, 2 by 4, and so on.
I think so too. 2 by 0, and then 2 by 4, and it should be this object here, and it is. And then it should be this object here, and it is. And after 3 iterations, we are out of the loop. All right, so now we can really take care of some computation. So, oh no, now we have to repeat everything for, first of all, it was A. Why doesn't anybody tell me that the input matrix should be A? Now we have to redo everything for L, even though M can be overwritten, but let's just make our life easier. We do L is the output. Thanks. Okay, so far so good. One more. Ga. Okay, what do we have to do? L10. Can I press 0? Yes. L10 is A10, L00 inverse. 10. Now it's M00. L00 inverse transpose. So okay. Whoa. Should we try that? I guess we can just try this. And let's go back to something easy. Then in the end, let's plot L top left. What did I do?
L top left is out of function, I guess.
No, L top left is fine. Input matrices have the same number of rows. What? L top left, top right, bottom left, bottom right, 0, 0, 0, 1, 2, 2, 2. Okay. Line 39. 39. At the bottom right, bottom right one. Here we go. No. Why not? ML 0, 0. Is a zeros? Yeah. What is complaining about? Input matrices in second row must have the second number of rows. Input matrices in second rows. Input matrices in second rows. Top left, bottom right, bottom right.
It's the problem is in that
It's what?
in the function.
Line 39.
Yeah, I know, but I'm trying to see where the matrices are created. Top left, top right, bottom left, bottom right. What are we doing? 0, 0, 1, 0, 2, 0. 1, 2, 1, 0, 2.
The only part of the matrix which is changed is this L10.
Ah, that's right. So maybe that's the problem. Haha, that's a problem. Thank you. So L10 equal M00. What's wrong with that? What's wrong with that?
M00 is supposed to be M10?
Say it again?
M10? I'm not quite sure.
Thank you. True. Very true. Okay. So we did that. but that doesn't really help us much because this is a 0 by 0 matrix. So let's continue. Let's update A11. So now it's M11. We have to update it with what we just computed, which is probably something like this. So M11, okay. Warning, warning. Matrix is singular. Yeah, okay, of course, it's a singular. And then now we just have to compute Cholesky, what we just did. I cheat and I put this. Okay. Sure. Okay. And now there is just one thing that should be correct here. And that is correct. That's the only thing that should be correct in this whole algorithm. No, wait, we wrote everything. So wait, everything could be correct. Okay, then we can even see. Whoa, it actually worked. First try. Okay. I tried not to print it. Yeah. Now I can't do that. Okay, and it still works for 20 by 20. Now we can do the test of a blocked algorithm. And it doesn't work.
Is Cholesky lower by default?
It's my Cholesky is lower by default. Why? Ah, not his Cholesky. Great. Thank you. Thank you. Very nice catch. Yeah, b equals 3, of course. Alrighty, we got an algorithm working. Now, I totally agree with you that we have done more than what we need, but the beauty of this is that these routines are general. If I give you any other matrix factorization, you can use the exact same routines. In fact, if I ask you to compute an LU factorization, you only have to change these 3 lines here. Everything else stays the same. And even if you want to solve a linear system, you only have to change stuff in here. The skeleton is the same. But I'm not going to fail you, you're right. This is more than necessary. So if you have something more elegant, I will show it. We can go ahead and implement the other algorithm just to show off, because now we can do everything so easily. By the way, I will make these routines available to you guys, so if you have to, in your whatever work, if you have to do some sort of linear algebra, you can use this for prototyping. There are similar routines in C as well, in case you need them.
They are available already.
I
found them on the website. I used them.
Oh,
That's why I was laughing.
how did you do that? Really?
Yes.
Are they available on
It
the...
was in paper, and in the paper there was a link, and I followed and followed and followed,
I see.
and there it was.
That's true.
How do you see the link? I haven't seen it. No, maybe I didn't get it.
So,
Before the references, I believe.
see, this is why it's difficult to teach computer scientists. So now what do we have here? We have M11, which is the exact same update. L11 is the same update, but now we work on different parts of the matrix. And so, as you can see, without changing anything in the skeleton, I can simply access different parts and implement a different algorithm. So here we need to work on L2, no, we update. So M21 equals M21, what is it? L20, L20, L10. L20 times L10 transpose. And then we have done that. What do we want to do next? Oh, we want to solve a linear system. So L21 equals M21 L11. I think it's this. Yes. Alrighty. Now I don't even go back to unblocked. I just try my luck. Blocked algorithms with block size 3 by 3, and it worked the first time. So this is when you guys should go, oh. You should be really surprised or appreciative. Very good. That's enough for my part of the solution. I don't think there was much more than this. It was about this recursive call. So recursive call, you cannot use CHOL, but you have to use your own code, but that's no big deal. Okay, now it's a matter of putting all of these into a function, and then you put the block size as argument. So, well, here it is, alg1 or 2, so you need a switch to do either this or that. So I think this is really most of it. Do you guys have comments or questions about this? Oh, you're right. That's a good question. Even if you didn't ask yet, but I think you're trying to say, what if the size is not a multiple of b? Yeah, that's right. That's exactly what you should do. So in the last, at each iteration, actually, you should have something that says b equals minimum between b and the size of the length of bottom right. Bottom right. Okay, let's try that. So what am I doing? If I am at the last iteration and I only have two, this block here, now it's only, well, no, the 2 by 2. The bottom right block is 2 by 2, and my block size is 3 by 3. This repartitioning would not work. So what I say, I always make sure that I don't try to get more than the remaining size of the matrix. So if I am good, this should work right away. I'm awesome. Come on. Absolutely brilliant. Yes, good point. Something else? No? Okay, how differently did you guys solve the problem? So you understand that you using the MATLAB notation after doing this 0, top left, bottom right.
Yeah, so I just define three variables because we have each quadrant is we have always submatrices, so I just the three variables, I0, I1, and I2, and then I access these matrices via this indices.
So what you're saying, you're really making use of the fact that we either have a symmetric matrix or triangular matrix. So you never need the top right part.
No, not even that.
Uh-huh.
I use that each block is quadratic.
Square.
No, it is square, yeah. Oh, it isn't.
That's true on the diagonal.
Okay, yeah, no, the partitioning on the rows and on the columns is the same, so I just need three variables. Otherwise, you would need six variables.
I
It's
see.
fine with partitioning.
Okay, I see what you're saying.
No,
Which means that A11 is always a square. Okay, anyway, I will look at your solution. Any other, something completely different or different? Well, if nobody did anything different, I should assume that everybody implemented it like this, which I don't believe.
The thing is, I use five.
You need 5 variables? 5 blocks?
Five for A1, A11, A21, and
5 what?
five, the 9 partitions,
Mm-hmm.
5 of them,
Ah, okay.
and 2 of the others.
So you're saying that you're not using all these 9 objects.
For A22, I just use the matrix itself.
Okay. Okay, that's fine. Because we never update A22. Okay, we never overwrite A22, so you can do that. Anything else? Should we go to Mathematica? Let's go to Mathematica. So, Graham Schmidt, I prepared a file. I did all of this by myself. Let's see. Style sheet, standard report. Okay. So let's start, let's go by examples. You can't see anything right now. Very good. So let's start by examples. We define inner product to be the dot, and the norm. The norm is always defined like this. So the norm we could even have a general definition that takes the function in as part of the definition of norm. But anyway, it doesn't matter. So what do we want to do? First of all, we want to take the first element and make it orthogonal. So we compute the norm, which is the length of this object, and then we take the object, we divide it by the length, so we know that in the end we end up with something that has length 1. If you don't believe it, if we do now norm of L1, too many square braces, that's 1. Okay, so we started from 1 to 0, and we just reduced the length of this vector to be of norm 1. That point, what do we want to do? We want to see how much of L1 is in L2. So L2 is some vector in the space, and I want to remove the component along L1 from L2. To see how much overlap there is, we do inner of these guys. And by the way, let's see if there is some overlap. There is some amount of overlap. That is how much of L1 I want to take out of L2. So I take L2 minus that times L1. Okay. Now I know that in L2, this new L2 doesn't have anything along the component, along L1. So these guys right now are already orthogonal. But I want L2 to also have length 1, so I have to normalize it. That's what I do over here. And so if now I say norm of L2, it's 1, and at this point I could show you that in of L1 L2 is 0, which means that these guys, even though at that point, okay, now I have orthogonalized it, but this means that the two vectors are orthogonal, and this means that L2 is it's unitary. Now we do the same with L3. We subtract the component of L1, we subtract the component of L2, and then we have some horror story. Well, not so bad, but if we simplify, it gets much better. Then we normalize this guy, and again it comes out some mess. But if we simplify, it's much better. And now we want to, okay, I don't know why this is here. Now we want to see if what we computed satisfies the orthogonality, and we have it. Okay, now we can be more ambitious and look at polynomials. I don't know why I'm doing this. Why am I doing this now? Okay, yes. So let's clear this. Now the inner product is completely different. It takes two elements, and how does it combine them together? Multiplies them together and integrates in the interval -1, 1. And you see the definition of the norm is always the same. Okay, GS is what I define. And I came up with this idea. By the way, this is the absolute first idea that I had, so maybe you guys have something better. I'm not claiming that this is very smart. Here we go. So my idea is the following. I will call GS, Gram-Schmidt, with 3 arguments. Left, right, and a function. And then I will use patterns to move through these objects. So what this means? R stays for right or remainder. This is what I still have to orthogonalize. And left is what I have orthogonalized so far. So let's use some patterns. G of left, when R is empty, what do you think this means? Maybe. Sorry? So R is the input list, yes. Let's put some underscores here. So in this case, what do you think it happens?
R is the input list, it should just return L.
Precisely. So this is the case that I see as a base case, the end of the process. My R is empty, so whatever I have processed has gone into L, so I just have to return L. This is the termination case. Now let's try something a little bit smarter, or maybe more interesting. We have L and R. Let's see, what do we do with this? R has some element and then the remainder. Probably 3 of them. Something like that. And then, okay, there is a still F. So what does this mean? It means that, it means that I am exposing the first n element of what I still have to process. has a triple underscore, which means it could be empty. So this could be 1, 2, but okay, the whole thing could have 1, 2, or as many elements as I want, but for sure at least one, because this guy only has one underscore. Okay, and at that point, what should I do? At that point, I need to take this element and I need to orthogonalize it with respect to everything else over here. So I need to do something like E f of, okay, E minus f of E comma L1 times L1, then minus f of E L2, and so on. Where L1 is the first entry of L, L2 is the second entry of L, and so on. And you see that this looks a lot like a map. I just repeat the same function. It's always the same. It's just that these guys are taken from this list. So I can map this thing over L, and then I just have to add everything together. That's an apply, and then I subtract. That's easy. Okay, but this is not enough to move this guy onto L, because in L we want the output, and so what I'm doing here is simply removing the components in the directions of whatever I have processed. After doing this, I have to normalize, but that's not a big deal. I just have to compute the norm of this. I divide by the norm, and at that point, I can shift this guy onto L. Okay, that's what I came up with. So here it is. Let's say that my right-hand side, my R, is empty, then I just return L. And basically, I want L to contain something. If both L and R are empty, I'm pretty stupid. So, okay, that. Now here. What am I doing here? So when there is an element, okay, when this guy is empty, so I don't have to normalize against anything, I just take the first entry, the first element, and I push it here after normalizing it. So you see, it's a recursive call, but this argument here has shrunk. And this is very important. It's a recursive function. So how do I make sure that will terminate? Well, the base case is on the second argument being empty. So my definitions should make sure that whatever I do, the second argument shrinks. So at some point, the second argument will get to 0, and I hit the base case. So that's very important to always keep in mind that this guy has to be reduced. So I had M and R, and now I only have R. And notice the triple loop, the triple underscore. And this is the important definition. When I do have something on the left, notice that it's a double underscore. So now I do have something on the left. I might have something here on the right, and I have one entry. Okay, and what do? This is the function that I just described. Function with our guy here, which is fixed, and then the second argument is varies, as well as the external argument. It varies, but notice that this is the same, tuck and tuck. and I apply this to all the entries in L. So this is what the map does, and then I add all of them together, and with this plus, then I subtract, and then I normalize. And the recursive call, once again, R is being shrunk. So this is very important. Here I normalize, and that's it. Okay, let's see. These are three different definitions, so that's not what you were asked. You were asked for only one function, so then we have to put everything together. But first of all, let's see if this works. So L, what is L? Okay, now we have 7 elements. My inner product is defined, we define that. And let's see if it works. I call Gram-Schmidt, empty left list, L as a right, and the inner product. Bang, and this is the solution. Let's see if it works. Looks like it does. Okay, now we can do something more. We can look at what the initial functions were looking like. And you see that they don't, even though you might not have much of an intuition of what it means for functions to be orthogonal, you see that these guys here are really not covering the space very well. They get closer and closer to something that is flat and then goes up. There is not really much difference between them. So let's look at what they look like after the orthogonalization. And you see how well they cover the space. They're much more spread out. All right, so here I put everything together. Now this is what I was asking you to do. GS of your name takes an input and takes an inner product. And over here I have the 3 definitions that I gave before. And then I simply call with empty left and whatever I want to process as right argument. So now let's do it again. This is a different, these are only 3 elements. Once again, it works. Now we change, no, the norm is always the same. We change the inner product. Now we integrate between a 0 and infinity. And now we're looking at exponentials. So minus x, 2x, 3x, and so on. Tac. Takes a little bit longer, but it's fine. Let's look at the functions. I guess here it's also interesting to look at what the exponentials would look like. Because once again, these functions are not orthogonal in the list. See, they're kind of monotone. There is no variety. So to put some variety in the exponentials takes some effort. That's why we got, stuff that is messy. Okay. Now let's continue. We have polynomials now. No, this is back to -1, 1. Okay, we have seen that already. I wanted to do, okay, this is an orthogonality on a different interval. And it's always the same. Okay, questions or comments? You
can use fold too, so you don't have to mess with all these patterns. So you can just fold it as
so wait, you're saying fold?
fold, yes.
Mm-hmm.
it computes, it needs a function and an initial value and a list, and then it gives you,
That's cool. Yeah.
so the initial value is the base that is already orthogonalized, and then you can add to this base from the list. That makes somewhat cleaner code.
Interesting. Cool. I want to see that.
So we define the input function before.
Yes. Every time you define the inner, you mean yeah, the input function.
I thought that we just input it and then define.
Input what? You mean the inner product?
Function itself.
How do you input it?
I just put it like input and it was defined when it's called.
Well, wait, but it is an input. In my GS, I pass it as an input.
Yes, but you pass only the name.
Yes, and instead?
I thought it should be like you pass the whole function.
Integrate AB and
Oh, but so you want to pass that.
as a pure function or
As a pure function, or that's right.
The whole thing, E, A, B.
the whole line.
Can you do that?
I did.
Okay. Okay, and how do you evaluate that?
But when I put it like in GS function input,
Uh-huh.
when I evaluate GS, the other function also evaluates.
But you take that whole string that is marked there, right?
Yes, and put it in GS.
Okay, I also want to see this.
How do you get a function out of that? You have, for instance, this double point equals sign in there.
Yes, that's what I thought. But
It works.
yes, no, the thing is, every time you just call when you call GS, the in function also is.
Gets evaluated. I am not sure I understand. I have to see what you did.
But the thing is, the other thing that didn't work.
Well, yeah, I'm not surprised. Other takes, comments? Let me see if I meet your approval. Was this elegant? Yeah, somewhat.
Folk makes it nicer because
Okay.
you don't have to use 3D function definitions. I have
Oh.
function. I have module with 3 functions, with 2 helper functions,
Mhm.
normalize and orthogonalize,
Mhm.
just to make them more usable, and then
Okay, I really want to see. I want to look at this. So maybe on Thursday we'll, between now and Thursday, I will try to see what you guys came up with. Hopefully, I have time. And now we have 30 minutes to scare you with the next assignments. If I find it. Homework 5. Here we go. Why is it not working? So it is a challenge. It's a C challenge. So I know that the computer scientists will have an advantage on this, but you know, computer scientists don't ever have a girlfriend. Computer scientists don't go out. We are code losers. So let them win a challenge. That's a little bit of a give and take. So what do I want you guys to do? I want you to compute Cholesky. This time you are on your own. You have to write a C program that computes Cholesky. And I want you to write the routine that goes as fast as possible. In fact, I want this routine to do a little bit more than just compute Cholesky. Let's go step by step. So the routine creates a symmetric positive definite matrix. This is easy. By now you know how to do that. It also creates L. So I am not asking you to overwrite A. I have to say this is possible. This is how it's done. But you guys can just create two matrices. One is empty, one is a symmetric positive definite, and you write the solution onto L.
We can or we have to?
You can. Oh, by the way, sorry, I have to jump right. I want to stop and say, how do you guys interpret this? Different teams than for the previous assignments, because somebody didn't understand that. How can I make it more clear? It means that if you were already in a team with somebody, you're not supposed to team up with them. Yeah? Is it clear? Okay.
So this means the team member should not be the previous one and the previous one.
Yeah, notice that there is an S here. Assignments. I knew that that issue would come up. Okay. But I'm also a computer scientist, so I do pay attention to these tiny little details. Yes?
And is this the final challenge?
This is the final challenge. It's not the project. This is a homework. Okay, so we have questions already? No? Okay. We have A, L, and we want to compute the Cholesky factorization. Okay. I want just one file, which is your name and then a final C.C. Then you will have the same, but with a different postfix ending. So this file, this program does a number of things, depending on how many arguments are passed. If you only pass one argument, this is the speed test. So what it does, it creates a problem of size n and solves it as fast as possible. This should be like the computational routine, the computational kernel. Okay, if you pass test, and here you can have 1 or 2 dashes, it's fine either way. Now you have to be smart. I want you to spit out a file. The file needs to be a MATLAB script. So the output of this C program is a MATLAB script. Is this difficult to do? No, not at all, because it just has to be a file with a .m ending, and inside the file there has to be something in the MATLAB syntax. Notice that I ask you to do something which is fairly easy. So you just have to put print statements that are readable, that write something that is readable by MATLAB. And this is the core of automation. This is something that nobody thinks about, but if you do this for a living, if you are in computational engineering, science, simulations, and so on, these kind of things makes your life so much easier. So I think it's good that you guys experiment with it. Okay, so test. What do I want you guys to do with test? I want to create a problem of size n, and you compute the solution, and you spit out on the MATLAB file, you spit out the definition of A and you spit out the definition of L. Is this something scary? I want to make sure that you guys understand that it's something very simple. How do we define a matrix in MATLAB? Something like L equal blah, 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 blah. This is already a matrix, vector or a matrix. How can this be a matrix in MATLAB? Very nice. Okay. Ba 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 ba. Da 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 da. This is also a matrix, right? So if you simply print something like this is a MATLAB script already. Just for your convenience, put this here, because if you create a matrix 100 by 100, then this really makes a difference whether you print it or not. So pay attention to these little things. But what I'm trying to say is that it might sound like, oh my God, this is scary. It's really nothing. Just use the printf statements, and that's what you have. That's what you get. Let's move on. So, test. What is the rationale behind the test? It's that you see whether what you're computing is the Cholesky factorization. It's difficult to do it in C, you do it in MATLAB. Okay, then we have something a little bit more advanced. I want to see how the performance of your routine behaves. So I do not want to see simply Paolo of 10 is whatever seconds. That doesn't tell me much. I want to see how Paolo behaves for 10, for 20, for 100, for 1,000, and so on. So this third part is to create a plot where I show the computation time. So on the x-axis I have different points, and on the y-axis I have a time, and then I have a line, and since the plot is self-explanatory, it would be nice to have maybe a title, it would be nice to have some labels and stuff like that.
How about some reference programs so that everybody can scale various timings and compare each other?
You are advanced, but wait for the next slide. That's too advanced. Okay, third part, that's what will be used as time to compete, to run the competition. I only want another MATLAB script that creates two vectors. One contains these ticks here, so 100, 500, 2,000. That's going to be one vector containing these numbers, and the other vectors will contain the corresponding timings. And I will use these arrays to compare to see who is going to win. So what you're saying as a reference comes out here. Everything will be run on my laptop, so that unifies it. Okay, so rules. Only the lower triangular part of A can be initialized and accessed. What does it mean? As we have seen in the MATLAB assignment, we never really worked on the upper triangular part of the matrix, so you are only allowed to access the lower triangular part. The input matrix is symmetric, sure, but you only store the lower triangular part. Likewise, your algorithm can only access the lower triangular part.
Question?
Yeah?
The matrix A is generated by ourselves, right?
Yes.
So we generate it, but we only use the lower part.
Yes. You generate it by storing, initializing only the lower triangular part. It's symmetric. Everything that you need here, it's already down here.
I just thought about the MATLAB style of generating that kind of matrix.
But this is C.
So do we assume that in the memory it's
Oh.
the lower rectangle, the triangle as well, or
Okay.
the whole square?
This is very, very important. Thanks for asking. the memory is still like this. So you still you still allocate a square matrix n by n, but you cannot touch all this area. No touch. Well, so what is it? Where is?
Allocate memory and don't use it.
This is how it's done, because in reality this part is used as workspace or it's used for other things.
The generation of matrix is still rent m plus n times
Sure, if you want, sure.
Okay.
As long as it's positive definite, I'm okay with it.
Initially? Okay.
Yes?
I'm fine.
When should the time start?
I say do not time the creation initialization of matrices, which means anything else, the actual computation.
Or to the write out to the n file, which will be
No, because as I said, the timing should be here.
okay, the other one just to verify.
Yeah.
And when you say that the empty part of the matrix is used for working and other things, but if we allocate that ourselves, the program can't really access that to use it anyway, can it?
Yeah, this is true.
So how does it use it?
I'm saying in general. I'm saying that generally speaking, when you do this, for instance, with BLAS or LAPAC, that's how it's done. You don't save up, you don't allocate only that part. That was a horrible sketch. I'm just telling you how things are in practice, not for this specific assignment. Actually, yes, for this specific assignment, if we go to the next one, you see there is a LAPAC, and that's how it's done. Let's continue. So only pure C, so no C++, C Sharp, or okay. No external libraries. I am not sure if every C has the square root. So if you need, the only exception might be the math library to perform the square root, but no other external library. Okay, except for timing, sure, and I/O standard lib. These things are obvious, but that's it.
So we can use the C standard libraries.
No, you can only C standard library.
What is
Library.
that? Yeah,
Yes,
yeah, for me.
sure.
Each is a library for me.
So I only want one file, and for sure you will have plenty of functions. Please organize them just in one file. This is also important. Everything will be performed, executed without any optimization, no parallelism. Yeah, creation, initialization, of course, doesn't matter. And this is important. Use different matrices A for successive iterations. So when you have to generate these vectors, and you have a matrix of size 100, matrix of size 200, 500, I do not want you to just create the largest matrix, maybe 2000 by 2000, and then do Cholesky of 100, Cholesky of 200, Cholesky of 500 as parts of this large matrix. That would create some caching effects, and that would speed up the program. I want you to, at each iteration, create a new matrix, okay? Dynamic allocation, freeing, all of that. Yes, I will check, code must be correct. At this point, I do not say what correctness is, but you can find it in many times. So you just make sure that it's correct. And again, if it's not correct, it's discarded. I will use my GCC and my laptop. You can use any other compiler because, nothing can be used. Basically, I prohibited all smart tricks, so that's it. Questions so far? Then let's go to the second part, which at this point should be super simple. This is a single call to a LAPACK. And maybe half of you or more than that right now are confused by this, but I'll try to show this on Thursday. So what I want you to do is to write a second function, a second file, sorry, second routine. Now it's called your name followed by a LAPACK. And what you do, you just created the matrix. Now it's only one. And you call a LAPACK to solve yet again the Cholesky factorization. Notice that it's only one because a LAPACK overrides the output. And the program does two things. If you only pass one number, it does that. If you pass three numbers, it does blah. Okay. So what is, if you only pass one number, it creates the matrix. It prints out the size of the matrix, this quantity here, which you have to compute somehow, and the execution time. If it's called with the three arguments, it returns a MATLAB script that does again this thing here. Okay? And then final rules, different teams, I have explained what it is. You only have two files, and the submission is at 1 p.m. so that I have some time to put together, to prepare the competition.
So about the printing scripts in MATLAB, it means that we cannot use the functions in MATLAB, or?
That's right. But why would you use functions? I just want a plot. So you just have to do. It's a script, you don't need functions. See you guys. It is on the cluster, and that's exactly why I want on Thursday, I want to show you how to access at least BLAS, and then you do it for a later. Thank you. Oh, that's right. But it's only 1.5 hours.
No, from 1 to 6 because they have strange.
Oh, now they are. Okay. Okay, good to know. From 1 to 6. Well, it's okay. I can just show what the script looks like, what the file looks like. Thanks for letting me know. See you guys.